Okay, I'm going to describe actually two programs we have with NASA. The one main one is a NASA sequential phase 2 based on previous work we've done on surviving the lunar night. And I'm also going to talk a little bit about the Viper rover, which we're also working on the thermal control system for. Next slide. So quick motivation are basically we're trying to develop a thermal toolbox that can be applied to lunar landers, rovers, and habitats. Go over the sequential phase 2 objectives, then talk about the two programs where things we're mostly developing on the current program, talk about the NASA Viper and some future work. Next slide. Okay, thermal management on the moon is much more complicated than it is for Earth spacecraft and Mars rovers. You have a 14-day long lunar night and lack of atmosphere, and followed by a 14-day long lunar day. So the astronauts actually in Apollo kind of cheated a little bit in that they went to the moon in the early morning, where you have the most benign environmental conditions. But of course, when we go back to the moon, we want to stay for multiple lunar day-night cycles. Now, we're mostly dealing with developing lunar landers and rovers right now, which are solar powered. So during the 14-day long lunar night, you need battery power to keep everything warm. The problem is that 1 watt over 14 days requires about 5 kilograms of extra solar cells and batteries. So that's part of the challenge. The other challenge is to survive the lunar day. So what we want is variable thermal links that can easily allow you to reject the heat to a fairly hot sink during the lunar day, but then passively shut down and use minimal or hopefully no power during the lunar night. Next. This is just showing a very simple thermal management concept where we're having a combined, showing pretty much everything thrown into one box. We have electronics that we're trying to keep cool during the day. So we have a thermal switch that activates. We have a variable conductance heat pipe that's also on, so we can easily reject heat to the radiate heat away from the rover or lander. During the lunar night, the thermal switch decouples, and the variable conductance heat pipe also passively turns off, and so we minimize the amount of survival heat. Next slide. This is just showing a little bit of how the systems require the differences between Mars, near Earth, and lunar day and night. We have solar during the day, batteries on overnight, and we have like roughly a 400 K synchrosoil temperature during the day and roughly 100 K during the night. Next. So the sequential phase 2 program, the objective is to develop a NASA, a high technology readiness level thermal toolbox, and develop thermal control systems, baseline designs for lunar landers and rovers. We have had a number of programs over the past 12 years that have been working on developing these kind of systems, heat acquisition, heat transport, heat storage, and heat rejection. I'll have a icon at the end of the program that you can take a picture of, and that'll give you take you to a web page that shows you links to all of the work we've done previously. Next page. Right now, on this program and in parallel, we're developing 6 additional components to enable lunar operation. The two things that we're doing on the current program is thermal control valves and a high power thermal switch. We'll describe both of those. We also have been working on several others, 3D printed loop P pipes, variable view factor radiators, improved wedge locks, and phase change materials for microgravity. Next. So the first system that we're working on now is what we call a loop heat pipe with a thermal control valve. And the way this works is that you add a thermal control valve in the system, and during the lunar day, the thermal control valve allows almost all of your vapor flow to flow from the loop heat pipe evaporator to the loop heat pipe condenser, and you might have a little bit of flow going back, but bypassing it. But basically, everything is open. You have a very high, good variable, good thermal conductance. Next page. During the lunar night, what you have is the thermal control valve directs almost all of the vapor flow coming from the evaporator right directly back into the liquid line and the compensation chamber. And what happens is, for a loop heat pipe to operate, the evaporator pressure must be higher than the compensation chamber pressure to give you the force needed to drive the vapor and liquid around the system. If we short circuit it this way, basically the two pressures are essentially equal, and the system passively shuts off. Next slide. So we have already demonstrated this type of system with a thermal control valve designed and manufactured by Pacific Design Technologies. I guess they're now Amatec. It's actually it's high TRL. It's currently used on several of the Mars Science Landers and several of the Mars rovers. It's a proportional valve, and it always has some liquid going either way. It works very well for that application. What we found when we built this was that it's somewhat overkill for our application. We really need only a simple on-off valve. Next slide. So we have two different kinds of designs. One's a closed one cold valve that just sits in the system, and as the condenser temperature drops, and it's going to start pulling down the evaporator temperature. But what happens is the closed one cold valve closes and prevents vapor flow from getting to the condenser. These are very good. We found these work well when we have a vertical orientation, with the radiator above the loop heat pipe evaporator. Next. We also have an open one cold design, and this is similar to the PDT valves in that when the system gets cold, the valve opens and short circuits the flow, the vapor flow right back to the compensation chamber. These tend to work a little bit better when you have a horizontal system. Next slide. Just showing our horizontal loop heat pipe test bed. We have the evaporator and compensation chamber on the left, and then we have a closed one cold valve, open one cold valve, and a number of bypass valves, so that we can test one or the other, or just have the whole loop heat pipe operating without a thermal control valve at all. Compare the three different cases. Next. So this is just showing an open one cold valve with variable power. What you have here is when the system is cold, the valve will be shutting off power, so you maintain your evaporator fairly warm. And what you see, the set point was minus 12.5 degrees C, and we gradually the blue line shows the blue line shows the aqua line rather shows the thermal valve, and as we raise the power up, eventually things get hot enough so that the valve opens, and we start seeing vapor going back to the system. Next valve. Next slide. We're also doing a series. We have a test rig set up to do endurance testing, where we have the valve set up here so that we can manually cycle them on and off. So far, we've demonstrated roughly 4,500 cycles with some of these designs with no malfunctions. Next slide. We're now working to develop a preliminary test plan to qualify our new thermal control valves. 3 testing systems, test stages: proof pressure, performance, and shock and vibration. Next. The other device we are developing now is what we call a two-phase thermal switch. Most thermal switches transfer heat by conduction, so you have something that is making and breaking contact, and you are conducting power through them. They're very good. They're used a lot in Mars rovers and all. But typically, they're designed to transfer like 1 watt of heat. What we want to develop and are developing is a two-phase thermal switch that can carry tens or hundreds of watts rather than just a watt or two. So we have a sealed bellows with a working fluid inside and a wick that's not shown. And when the power or is low, what you have is the vapor pressure is low, so the valve stays, the bellows stays in a compressed position. As you start putting power into the system, you warm up the pressure, with the temperature, the vapor pressure increases, and eventually the bellows will expand enough so that it will touch the heat sink and you can reject heat. We've actually find it works in two different conditions: an actual thermal switch, or when things get very cold, it disconnects, and as a variable conductance device, where if you're in a certain range, basically the valve, the bellows just kind of oscillates back and forth and allows you to reject heat with a constant at a constant temperature. Next slide. So we've been conducting some initial tests, and what we've done is the bellows, the thermal switch is shown in an open condition in the on the left photograph, and what we have done is attached a thermal resistance, electrical resistance measurement, so that when the valve is on, the metal makes contact, you get a very low thermal resistance, and when the valve is off, we have a the bellows retracts, and the thermal resistance goes higher. It's set by a resistor in parallel. Next. Next one. And next one. So this is just showing some of our initial test data where we are heating the system up. And what happens was when you get to rather I should say cooling the system down, when you get cold enough, the bellows actually detaches. You can see the green line, the green square wave there. That's actually the resistance goes from low to high as the bellows detaches, and basically it helps maintain your temperature of your evaporator because you're not dumping any heat to the condenser. Next slide. We're currently working with Astrobotic to develop a simple thermal switch device for a cube rover. This is actually a very, very tiny system. It's only designed to, it's very small, 10 centimeters by 20 centimeters is kind of the typical dimensions. And we have something that will turn on or off depending on whether you're trying to dump heat or conserve heat. Next slide. So this shows our basic design concept. Currently, the electronics are mounted on the heat collector plate. And what we've done is added a bellows thermal switch and a radiator above that to radiate when the bellows is connected and conserve heat when the bellows is not. We have very low conductivity standoffs, and we actually have a heat pipe spreader that helps spread the heat, but also is needed to add rigidity to the system when the bellows are pressing against that very thin face sheet. Next slide. Just showing our estimated on and off conductances going from about half a watt per degree K when it's on, to somewhere between 10 to the -3, 10 to the -4 watt per K when the system is off. And just showing the system setup here and the location of the systems, and kind of with a 7-watt case, we have a maximum temperature of 62 degrees during the lunar day, but then we can conserve heat during the lunar night. Next slide. We're also currently doing some work on another program, the NASA Viper rover, volatile polar exploration rover, and it's a lunar rover tasked with investigating the southern polar ice cap for water ice. It's equipped with a large number of controllers, etc., and a drill to investigate the ice. And we are designing and fabricating the rover's thermal management system. Again, it's got to be designed for the hot case when you're operating and trying to radiate all the power, and the cold case, which is during effectively the lunar night. This is actually not a true lunar night. The around the South Pole, you have mostly daylight, and this is more when we go into a cold crater for maybe an Earth day or so to drill for ice. Next. This is just showing the Viper lunar rover with the thermal to the left and the thermal control system to the right. We have radiator panels on the top, loop heat pipes with thermal control valves, and then there's a warm electronics box, that gray box at the bottom, and we have a series of constant conductance heat pipe embedded panels to transfer heat from the electronics to the loop heat pipe evaporators, and then the loop heat pipes transfer heat up to the radiator panels. Next. So there's 5 loop heat pipes total in the NASA rover. They're with use propylene as the working fluid. I have thermal control valves, the Pacific Design Technology version, and again the thermal control valves passively control the vapor flow, shutting it off during the lunar night and opening up during the lunar day. So it reduces the power loss to the via transport lines to single watts, which is very significant because, as I said before, every 1 watt of power is about 5 kilograms of batteries and solar cells. Next. So future work on the NASA sequential program, we're developing rover thermal control valve systems and thermal switch systems at ACT, and then we plan to we're fabricating and validating these test devices, and then we're going to work with Astrobotic to design a thermal control system for a lander mission, fabricate and test an engineering design unit, and do the same things for a small rover. And finally, we will build flight hardware for a NASA selected application. Next. Just want to acknowledge research was funded by a NASA sequential phase 2. Technical monitor is Jeff Farmer, had Dave Bugby of NASA JPL, and a number of people from Astrobotic helped with suggestions for this program. The ACT engineers and the ACT technicians are listed. Next. And just leave this up for a minute. If you take a picture of this with your cell phone or whatever, it will take you to a link that discusses some of the programs, the previous programs that this sequential phase 2 is based on. And that's pretty much it for me.